just so you feel like you're getting your money's worth this semester. What we're going to talk about today is the NRCS rainfall runoff model. And the homework assignment is relatively quick turnaround on this one. There have been some assignments where I've combined big ideas together and other assignments like this one where it's a pretty narrow focus and a lot less effort. So I think homework 7 won't take you as long as some of the previous assignments have, and it's due on Monday. Now, with the NRCS rainfall runoff model, what we're going to be doing is trying to work towards a method that will allow us to predict the runoff when we don't have a unit hydrograph available. A unit hydrograph is very useful if you've previously taken runoff measurements in a watershed, but there's the vast majority of watersheds that you're not going to have any actual runoff data for. So remember, I think previously I've suggested that we could distill this whole course down into a single big question. And if we did, that question would be, for a watershed or an area that we're interested in, what are the runoff characteristics, meaning the amount and the timing? And how might they be changing over time as a watershed is being developed? And the inputs to this question include the rainfall characterization, the abstractions, like in the watershed, how much interception might there be as the seasonal vegetation changes, or how much surface wetting is required before the water begins to flow over the surface. And the infiltration, that's having to do with the moisture content of the soil characteristics themselves, like the suction head and the hydraulic conductivity. So we've talked about a lot of the theory behind all of this that is going to feed into the NRCS model. And we wouldn't need a model if we had direct observation for every watershed, but we don't. Because what we're going to want to do is we're going to want to predict the rainfall runoff response and have a hydrograph shape so that we can do things like size ponds, so that we can size culverts, so we can know the flow of water that's entering channels to identify how deep the water is going to be and which homes are maybe at risk of being flooded. So having a model is a very important thing because there are so many physical infrastructure consequences that have to do with excessive stormwater runoff. We also want to be able to account for the delay and the timing consequences of routing. And routing has to do with the travel times. The travel time not only of the water flowing over the surface, but also when the water enters a stream, it's going to take a certain amount of time for the water to pass from an upstream channel through a series of perhaps meandering creeks and progressively increasing in size rivers before it finally gets to an interesting point for us where there's maybe a bridge crossing or water's being withdrawn for industrial uses. So we need a model that will account for all of those effects. And the implications, the hydraulic sizing of culverts, knowing what elevation bridges need to be built at, but then also when you look at human development adjacent to rivers and creeks, if we know what water elevation the river is at, then that tells us what's the probabilistic risk that an area is going to be flooded. And that can tie into the cost of insuring property that's adjacent to rivers. It can tie into things like the home loans that people can get for a property because of the risk of flooding. So there's a lot of economic consequences in addition to human health, human safety. So the big question is, what's the hydrograph going to look like for a certain storm? And since we don't have direct measurement of the vast majority of watersheds, we have to have models to synthesize a hydrograph based on an estimate of the rainfall that we may expect to see. So this is what the NRCS method is working to do. It's working to connect the dots between rainfall and runoff. And so the rainfall temporal distribution, if we know the depth of rainfall, so maybe a 24-hour storm and a 100-year return period would have a depth of, let's say, 5.6 inches. We could use the SCS rainfall distribution to tell us during a 24-hour period how that depth translates into intensity. And then when we have the intensity, we can put it through a model that is going to give us the runoff as a result. Any questions so far about what the NRCS method is trying to accomplish? So just graphically, we start with a rainfall hyetograph, and we need some sort of a function or a process that will translate the rainfall into a runoff response. And what the NRCS method does is it tries to account for all of these physical factors. The NRCS method tries to account for what kind of soil is in a watershed, what sort of surfaces are on top of that soil, whether it's impervious surfaces like roofs or concrete or pavement, or maybe if it's crops, how that's affected the infiltration capacity of the soil. The NRCS method is trying to account for surface wetting and ponding that could occur, the slope of the ground. Remember, we've talked about how steeper slopes allow water to move more quickly over the surface, and as a result there's going to be less infiltration generally. So the NRCS method's trying to account for that, the stream density, the sinuosity of streams, the watershed geometry, like how long a watershed might be or how circular it could be. And so there's all of these physical factors we've talked about, and each of them can affect the relationship between an amount of rainfall and what the runoff characteristics look like. And so it's a really complicated set of factors, and what we want to do is we want to make this method easy to use, but also somehow sensitive to each one of these factors. And so it's a balancing act where we don't want to make it so that so much data is required that you can't actually generate the model because there's a lack of data for an area of interest. But at the same time, if we ignore some of these input factors, then the model isn't going to be accurate. So you're balancing model accuracy with ease of preparing the model and how much data is required. So the NRCS method, what it does is it begins by looking at the soil and the land use characteristics, and based on that, calculating something called a storage parameter. And so the storage parameter is going to tell you a depth, and so it's measured either in inches or centimeters, a depth of precipitation that could be stored and retained by the watershed. And based on that storage, you're going to also estimate the initial abstractions like the retention in surface wetting, the retention of water in small ponding, and from that, calculate the amount of rainfall excess. And then once you know a depth of rainfall excess, distribute it temporally into runoff using a temporal curve similar to what we did with the SCS method. Remember, the SCS method says if you have a rainfall depth, you can translate that into the rainfall over time. Well, there's a similar curve for hydrographs where it says if you know the runoff depth, in other words, if you've estimated the rainfall excess, then there's an approach to translate that into the runoff intensity over time. So we're connecting the dots with the NRCS method. Now, here is the curve of declining potential infiltration. And we've talked before why at the beginning of a storm there's a high rate of potential infiltration, and it's decreasing over time as the soil voids become filled with water, the suction pressure decreases, and the rate of water that's going down into the soil decreases over time. So we've overlaid that figure of declining rate of infiltration on top of a rainfall hyetograph. And so this rainfall hyetograph is just at the beginning of this hypothetical storm, there was a certain amount of precipitation, and the precipitation rate went up, it went up again, then it decreased. Now, the area under the curve is the amount of water that's going to stay in the watershed. The area above the curve is going to be precipitation excess. So here the P sub E stands for precipitation excess or rainfall excess. We sometimes also call it runoff, but that can be a little bit tricky because most of the time when we use the word runoff, we're thinking in terms of volume per time. But in this formula, the NRCS method and each of these, it just has units of length. And so the initial abstraction, the water that's just stored in the catchment but not necessarily infiltrating. This could be the surface wetting and the interception. The initial abstraction is going to be at depth. And of course the units for precipitation is going to be as a depth as well. And so what we're saying is that if you multiply the width of this, which represents a time, by the precipitation rate, you get a certain amount of rainfall. And so the area under the curve is the amount of rainfall that is stored in the watershed. What's above is the excess. And so with this overall method, you can see that the precipitation is split up between the precipitation excess, which contributes to runoff, the initial abstraction, and then the stored water, the retention. And that's mainly infiltrated water. So F sub A here is infiltrated water. And the idea is that the ratio of the water that is stored with the potential maximum storage is similar to the ratio between the amount of rainfall excess to the overall precipitation minus the initial abstractions. And we'll go through what the implications of that are, but that's kind of the NRCS method distilled down into its pieces, is that it's the actual amount that's stored by a watershed relative to the potential amount stored is the same as the precipitation excess relative to the precipitation minus the initial abstraction. And the initial abstraction, it's pretty common to just assume that it's 20% of the storage parameter. And the storage parameter, we're going to estimate that based on what kind of soil we have in the watershed and what's on top of the soil. So S, we can go to tables to calculate based on what's called a curve number, but the initial abstraction, we don't have as precise a way to estimate that directly, and so just as a placeholder, it's common to assume that initial abstraction is 20% of storage. Okay, so if we think about this in terms of mass balance, remember mass balance says that there's in and out, and then the difference between the two is accounted for by accumulation inside of a watershed, and that can also be a negative accumulation if, for example, groundwater is seeping out and contributing to base flow in a stream. So the watershed has the initial abstraction and the retention that's accounting for the accumulation. What comes into the watershed is the rainfall, and we will measure that in depths. The outfall, the outflow is going to come out in units of centimeters or inches. The formulas I'll show you today are going to be in units of inches. And so sometimes it's strange to think of the outflow from a watershed in terms of inches, but you could turn it into a volume by multiplying it by the area of the watershed. And so, you know, if you have 1 inch of rainfall excess and you know the area of the watershed in acres, then the volume could be calculated just by multiplying the area of the watershed by the rainfall excess depth. Now, I mentioned curve numbers earlier, and that's what we're going to look up off of tables, and we use curve numbers to calculate the soil storage in inches. And so the soil storage, remember, is kind of a maximum amount of water that could be stored inside of a watershed when you account for essentially how much infiltration is going to occur. So once you have the storage estimated with this curve number parameter that we get from a table, then this is the NRCS equation. It says that the rainfall excess is going to be a function of the precipitation depth, the storage parameter, and then assuming that the precipitation is big enough to overcome the initial abstraction, so 0.2s is the initial abstraction, then we'll get the precipitation excess with this formula. But if the precipitation depth is less than the initial abstraction, we just assume that all of the precipitation is just used up in surface wetting, interception, short-term evaporation, and so then there wouldn't be any rainfall excess. So we don't use the equation if we don't exceed the initial abstraction. This only applies when you are exceeding the initial abstraction. Before we look at this example, I want to show you some tables for curve numbers. I'll jump to these real quickly. So curve numbers are based on 4 different soil classification and an almost infinite number of different land use categories. I show you here in the slides 2 different curve number tables, but there are a lot more than just these, and they're in a lot of different publications by the Department of Agriculture. Textbooks have estimated curve numbers, and you can actually calibrate your own curve numbers for watersheds as well. But the general trend is that hydrologic soil group A is a soil that's very sandy and well drained. And then at the other end of the spectrum, a class D soil would be one that's really plastic, it swells, and really poor at transmitting water. And so the general trend is an increasing curve number with a decrease in the infiltration capacity of the soil. And so what that means is if we go back to the equation for how we're going to use the curve numbers, all right, so we're going to use the curve numbers here to calculate the storage. And so if you have a big curve number, then that's going to decrease this first term, and when subtracted with subtracting 10 from that, storage will be small. But if you have a small curve number, then the maximum storage is going to be much higher because more water is going to be infiltrated. So back to this table briefly, just so we can understand the trends. The other factors that are accounted for in tables like this is the density of vegetation. And so you'll notice here for lawns, there's 3 different categories of lawn. There's good condition, where the grass is covering more than 75% of the area, fair condition, and then poor condition, where the grass is covering less than 50% of the area. And so the more vegetation there is in this watershed, they are decreasing the curve number, which is going to mean that there's more infiltration. So you can kind of think of, if we're going to assign a value judgment here, a high C value or a high curve number is bad, because a high curve number is going to have lots of runoff, and when it comes to modeling stormwater runoff, that's when we're usually thinking of water as in terms of its potential for flooding and the scour and the problems that it causes. And so the more developed an area is, the higher the curve number is going to become. And we see that also here with the impervious areas. So here in industrial and commercial areas, as the percent impervious area goes up, so they're saying, like, if it's townhouses or maybe condos, you'd have 65% of the top view area is impervious, and the remainder would maybe be green space. And so for a good Class A soil that's well drained, you'd have a curve number of 77, but the more impervious area you have, the curve number is increasing, which means that there would be progressively more runoff as you have a higher impervious area. So urbanization will inevitably increase the curve number. And here for paved areas, you'll notice the curve number is 98 regardless of what soil you have. So it doesn't matter if you have concrete on top of sand or concrete on top of a plastic swelling clay, there's still going to be the same amount of storage, which is to say very little for that material. All right. So now that we've talked a little bit about curve numbers, let's skip back to this example. And I'd like you to try and see if we had calculated a composite curve number for a watershed, and the curve number was 70, then how much rainfall excess would we expect if there's 0.7 inches of rainfall or 3.5 inches of rainfall? So this 0.7 and the 3.5 is P. So the process that you're going to go through is calculate storage based on the curve number, and then calculate the initial abstraction. And remember, the rule is that this formula for P sub E only applies if the precipitation depth exceeds the initial abstraction. And so if the precipitation depth is bigger than the initial abstraction, then you use this formula to calculate the P sub E. And that's what we're trying to figure out, is kind of like how much rainfall excess is there going to be, and where's the water in both of these two cases.
Again, most of the cases are 80% are non-lethal, but it's a mild case.
Yeah. All right, so we're trying to figure out in these two scenarios what happens with the watershed. So what we find is 0.7 inches is going to cause no runoff, right? And this isn't the right one. Oh, yeah, it is. All right, so 0.7 inches, we'd have a maximum storage of 4.286 for this curve number. And so the initial abstraction is going to be 20% of that. So since the initial abstraction has to be satisfied before there will be any excess, in this first case of 0.7 inches, there's not going to be any rainfall excess, which means there wouldn't be runoff. So any questions about that first part with 0.7 inches of rain? But if there's 3.5 inches of rainfall, then now the precipitation is bigger than the initial abstraction, so we will see an excess. And so there should be 1.008 inches of precipitation excess. So it takes 3.5 inches of rainfall to get 1.008 inches of rainfall excess. That means that all the rest of it must be retained and tied up in the initial abstraction. So we can do that calculation and solve for F sub A. Now remember, back to our definitions, F sub A is the amount of water that actually is infiltrated. S is a potential. It's the maximum amount of storage that could occur. But you're not going to have all of the water infiltrating. Only a fraction is going to infiltrate. And so, potential storage is one thing, but if we want to find out the actual amount of retention, we can substitute in the storage quantity that we have, the precipitation excess that was calculated, and find out that 1.635 inches is going to go to retention, which is mostly infiltration. So of the 3.5 inches, we can add it all up, and we can see that here's the initial abstraction, the retention, and the rainfall excess, and it does balance to the same 3.5 inches that we initially started with. And so it's kind of giving us an idea of a certain size storm in this watershed that, the curve number of 70, that's actually about the curve number of most watersheds around here. I've done a lot of work across the state, and maybe there will be a rare watershed that has some sandy soil in it, and the average there maybe would be 68 on a weighted basis. And there are a few watersheds that have extremely clay soil, or maybe they're a little steeper than usual or have rock, and so maybe it would be in the mid-70s. But 70 is a pretty typical curve number here in West Virginia, and so that would give you a sense for a storm depth of 3.5 inches, how much excess you're going to see and where the rest of it's going. Okay, so that's all the time we've got for today. Just remember that this assignment is going to be due on Monday, and what we've just gone through, this same kind of calculation, is part of the homework assignment, and so maybe you could get an early look at some of those problems, and we'll continue talking about this model in class on Friday. So I will see you then.